Again to MECH 314 Fluid Mechanics lecture. We are continuing our Navier-Stokes equation. We said last time that the second step after we have derived it and after we have defined our boundaries and domain is to simplify the Navier-Stokes equation, as we have done in this example. And once you simplify, you integrate, and when you integrate, you will eventually end up with constants of integration. And for you to be able to get those, to evaluate them, you need to apply your boundary conditions to get the constants of integration. So that's the last step, well, or the step before last in the Navier-Stokes equation analysis is to apply boundary conditions. So let's talk about boundary conditions. This slide is quite important because it will it has all the boundary conditions that we are going to use in this course. So let's start with the first boundary condition. We have a solid boundary at the bottom. These are the obvious ones, and we have a gas-liquid interface at the top, and eventually we close our boundaries because we need not to simulate the whole flow in the universe, but we need to have some finite fluid to work with. And we're interested in the fluid that's inside this boundary. This fluid between those four boundaries has a density and viscosity of a Newtonian fluid. This is what we call the domain of our fluid. So let's talk about what type of boundary conditions we get at each one of those four boundaries that we have gotten. So boundary conditions would be on pressure and velocity, because if you remember from our previous equations, the independent variables in the Navier-Stokes equation are the x, y, z, and t, but the dependent variables are the pressure and the velocity in its three components. So the boundary conditions would be on the pressure and the velocity. So let's go back to your partial differential equation course, and you remember you had two types of boundary conditions, Dirichlet and Newman. So in the first one, you have the value of the function at the boundary. So in this case, we have the value of the pressure or the velocity at one of our boundaries. And the Newman type boundary conditions, you have the gradient of the velocity or the pressure at that boundary. So the first boundary, well, we have, let's look at the inlet. So we have two types of boundaries here, inlet-outlet boundary conditions, where we really need to supply the velocity as well, the magnitude of the velocity and the pressure at the inlet and the outlet. We're not dealing with the energy equation, so the temperature is not something we're going to cover in this course. And this type of boundary condition is the Dirichlet one. Similarly, at the bottom you have a solid surface, and at the solid surface you have the no-slip condition, which says or stipulates that the velocity of the fluid particle that's in touch with the solid boundary has the same velocity as the solid boundary. So you have equality of velocity. So the velocity is known over here, and again it's a Dirichlet boundary condition. This is an impermeable wall, so all three components of velocity of the fluid will be equal to that of the solid. The third type of boundary conditions is associated with a free surface. So, for instance, the interface between water and the atmosphere, or oil and alcohol, or oil and water, two immiscible types of fluid. And at this interface, we can write, actually we are interested in two boundary conditions. The first one is the velocity, the vertical velocity of the interface. So the interface height, which is the wave height, if you will, is measured by a quantity eta. So the vertical velocity of this wave has to be equal between the liquid and the gas on the two interfaces, on the two sides of the interface. It's a positive displacement type of pumping or motion system. The second type of boundary conditions at the interface will actually be the equality of shear stress. We're not going to be dealing with the heat, and we're not going to be dealing with surface tension because we have skipped that in chapter 1, so we don't really need to worry about that. So we are interested in the shear stress, and the shear stress on the air side of the interface will have to be equal to the shear stress on the liquid side of the interface. And the shear stress is defined as the viscosity multiplied by du dy. We'll have a couple more words on this in the next slide. So the shear stress needs to be, so the shear stress on the gas side has to be equal to the shear stress on the liquid side. And if they weren't equal, just because the interface, we're making the assumption that it has zero thickness, the fluid particle at the interface will have an infinite rotational speed, which is not, if these weren't equal, and that would not be physical. So that's where this condition comes from. So let's talk about shear. So these are the types of boundary conditions. Here we've talked about at the inlet outlet, as well as the solid boundary. We've talked about a Dirichlet boundary condition, while the equality of shear stress is actually we're supplying the gradient, because the shear stress is the gradient in the velocity multiplied by viscosity. So that's a Newman boundary condition over here. And for the interface, you have the boundary conditions summarized by an equality of shear and an equality of vertical velocities. The vertical velocities is easy to understand. As we said, it's a positive displacement. While the shear stress equality, we want to now talk about a little bit more about what we mean by shear stress. So shear is friction. So it's the rubbing force between the gas and the liquid against each other. And now let's talk about the directions of that. If you go to the derivation of the Navier-Stokes equation, we had this type of cube. And on each face we said we had two shear stresses and one normal stress. So we're particularly interested in the shear stresses. So sigma yz, and that's sigma yz, that's sigma yx, and so on. So we're dealing in this course in cases where we only have one of the shear stresses. As you can see, we said we have 6 faces, and we have 6 times 2, we have 12 shear stresses on these faces, but 6 times 2, so here we see the 6 and they repeat on the other side. And we are making the assumption that only one of those is non-zero, or all of them are actually, in the case of an interface, one of them is non-zero and the other 5 are actually 0. Just to make our life easy. Now, in a more general situation beyond this course, where you have all 12 shear stresses to be, or 6 shear stresses to be non-zero, then I would advise you to go back to slide 41 to be able to, that's what you're going to see, to be able to compute the value of the shear stress on the interface. And there is a great link in the description below on YouTube, and in that document you will be able to see on page 11 to 13, it has a very, very detailed derivation of how these rheological properties came to, for a Newtonian fluid came to be. So make sure you check them out if you're interested. But that's beyond the scope of our study. And what I would like you to remember here is that let's look at the tau yx. That's the shear stress on the y face. So it's this particular face. It's the one perpendicular to the y-axis in the x direction. So that gives us the direction. So it's just how to compute it. So that was the question from the previous slide. So on face y in the direction of x, the shear stress will be equal to the gradient of the x velocity in the y direction, so du dy. And you will see this, I've colored them so that you can do it for any type of problem. If you have a non-familiar coordinate system, if I flip the yx with zy, you should now be able to look at your flow, see where your flow is going, and see where the gradient is pointing and velocity is pointing. But suffice it to say, or to just to give you a physical feel of this, you need to remember that shear stress is friction, and friction is always going to be in the opposite direction of motion. So and then the gradient will be in the direction perpendicular to the velocity. So y is in the velocity is the direction perpendicular to u, x is the direction perpendicular to v, and here to w. So you get the idea. But remember, one thing is that friction is in the same but with a minus with a negative direction in the same alignment with the velocity, but in an opposite direction. So that's why it's called friction, and it's shearing kind of stress. So that is on boundary conditions, and this is the we will need those types of boundary conditions when we are talking about interfaces. And now we want to solve our Navier-Stokes equation. So we have derived them, and what the Navier-Stokes equation describe the 4 equations of 1 continuity and 3 linear momentum describe the conservation of mass and momentum inside our domain. So first thing is we want to define our domain where our fluid is. So in this case, we're drawing this cube, and in that cube we're simulating the flow around a car. So our car is part of our boundaries. So we have the external boundaries, we have internal boundaries, and the fluid domain is what's in between the car and between the outer boundaries that we have. And then we can decide to define what are the appropriate dimensions of our boundaries. And the flow inside our domain is described by the Navier-Stokes equation, is dominated by that. Don't forget about your coordinate system. It's quite important. So I now have defined my domain, defined my boundaries, and now I have written my boundary conditions. So I have inlet, outlet, maybe I have a solid boundary here, maybe this is a wind tunnel. I also have solid boundary type of boundary condition on the car. I simplify the Navier-Stokes equation if they can be simplified, and then I integrate them. Then I get constants of integration, and then once I got constants of integration, I apply the boundary conditions that I have at the boundaries, and then what you want to do is to you get the solution of the velocity and pressure, but then you have the velocity and pressure at each and every point in this XYZ cube. And how do you see it? How do you visualize it? There is one way is to either have a function, u is a function of x and y and z, or just graphically plot it as you can see in this picture, so that you can make sense of it as engineers. So that is a general overview of the Navier-Stokes equation. Now let's do a real problem now.